Thank you, everybody, and thank you so much for asking me to be here today. To dive right into things, before I talk about GIS for a little bit, I'm going to just mention a few things about Argonne, since it's so close, and there are a lot of opportunities for potential collaboration between COD and the community and Argonne. And in fact, Dr. Rondeau and a collection of faculty members came out to the lab last April, I believe, and had a lot of meetings in the hopes of forming a stronger relationship between the two entities. So Argonne is our nation's first national laboratory. Its origins go back to the Manhattan Project from World War II. The group of scientists were working under, I believe it was the squash field or the football field at University of Chicago, trying to get their nuclear reactions to work. And then when they finally did, they realized, oh, we're actually in Chicago. Perhaps we should do this in a place where there aren't millions of people. So they moved 25 miles outside of the city to just about to our current location. And of course now it's surrounded by people again, but there's no more research into weapons, or there's still research into peaceful ways for using nuclear materials, but in much, much smaller and safer quantities than there used to be. So now we are a multidisciplinary laboratory that has more than 15 different research divisions in just about any field you could imagine, from national security, nuclear engineering, biology, environmental science that I'm going to talk to you about today. We have many users who come in every year just to use our user facilities. They're not regular employees, who use the advanced photon source, which is the giant light X-ray that we have. It's that big circle in the bottom, on the lower left-hand corner. We have Mira, which is one of the Department of Energy's top supercomputers that anybody can write a proposal to request time to use. And we've got several other user facilities. And another reason that I wanted to talk a bit about Argonne is that I'm here at a local college, and we have a ton of educational opportunities every year. Most of them do happen during the summertime, but there are quite a few internship programs that happen throughout the school year as well. We have I'm not going to go through all of these, but some of the ones that might be of most interest to you if you're looking for an internship now or sometime in the future, or want to share with your students, are the Science Undergraduate Laboratory Internship, or the SULI program, and also the Community College Internship. Those are both for undergraduates, and they're open to just about anybody who, I don't even know if there's a GPA requirement. I think there's just an age requirement. And then for people beyond their undergraduate degree, there's also programs for people who are in grad school or getting their PhD. So if that's something that interests you, there are lots of internship opportunities at Argonne. And you can get more information at these links below, or if you just go to Argonne's main website, which is anl.gov, and navigate to the education page. This is just a little bit about me. I wanted to add, since I am here at College of DuPage, between getting my bachelor's degree and my graduate degree, I actually came here for classes at COD. So if anything today interests you about GIS, I actually got my start in GIS taking the classes that COD offers. And also, since I'm here and I'm the program initiator for WIST, I just want to talk a little bit about that too, because we do also try to do a lot of work with the community. So the overall mission of the Women in Science and Technology program is to provide leadership and to promote the success of women in science and scientific and technical positions. It was started over 30 years ago in 1990 because the women at the laboratory realized that they needed a network. there were the number of women was quite small, and they felt like they needed a solid organization to help them advance in their careers and just meet other women across the laboratory. And the program has definitely grown over the years. And now, aside from working on internal topics and issues for women currently working at the lab, we're also doing a lot of outreach to encourage young women to pursue careers in STEM. I mean, I personally think everybody should pursue a career in STEM, male or female, but there are a lot of studies out there that still say, you know, certain things happen when girls are still young in school, or something happens that discourages them from pursuing something in the sciences or engineering, even if they're interested in it, or they just feel like they're discouraged and they can't do it. So we try to promote to young girls that's a possibility for them. And we do that with 2 outreach events every year, one for high school women and one for middle school girls. And if anybody's interested, I can provide you more information on that after the talk. And now into the reason you're here, Geographic Information Systems. So, excuse me. Quick survey of the room. Has anybody here heard of Geographic Information Systems before? Awesome, okay. No, that's usually more than I get in a room, so this is cool. Okay, and it's something that is really not familiar to a lot of people, especially the term Geographic Information Systems. So of those people that have heard of it, have any of you studied or have any plans to further study GIS? Awesome. Are you currently enrolled in the GIS classes here? Do you have Joe?
Yes.
I had Joe, and then I worked with Joe, and he still works at Argonne. We're in different divisions now, but cool. Oh, that's so exciting. The program lives. Excellent. Okay. So I'm so excited. Usually I talk to a lot of students. So in general, I don't talk to a lot of adults about this, which is exciting for me in general. And to talk to adults that have actually heard of this before, I'm very excited. So a Geographic Information System, the official definition is it's a computer information system that can input, store, manipulate, analyze, and display geographically referenced data to support decision-making processes. And some of the important parts of that definition are, you know, geographically referenced data, and that's what sets it apart from looking, you know, from being a data scientist that works with, you know, giant databases worth of information. And so yes, and geospatial data has not only just that geographic, you know, Cartesian XY location, it also, the file structure allows us to store all sorts of tabular information. Think like an Excel spreadsheet or an Access database, which allows for not only spatial analysis like area and distance and proximity, but all sorts of more detailed, in-depth analyses. So to break it down a little bit, or to make it more, because I know the definition is complicated, especially when it's not something that you're familiar with. And so it's really sort of like Google Earth or Google Maps plus a SQL or an Access database. It's sort of the power of both of those combined into one thing. There's a robust storage system that can handle terabytes worth of data. There's a whole bunch of spatial analysis tools. I'm not sure if I'm going to get into too many of them today, but there's oh gosh, there's so many. Like I mentioned, there's proximity. There's a whole separate extension, and there's a whole specialty of geospatial statistics. So running regressions, or I'm trying to think of other statistical terms that I know. I'm blanking on all of them right now. But things like regressions or ordinary least squares or other of your standard statistical analyses, they've been adapted to also be useful for geospatial data. So you can add that spatial location component to your statistical analyses. There's also new tools that come out every year that add the time component. So not only can you analyze, the location of something, but if you have a good data set, you can also look at how something has changed over the course of time. The best, and I think most succinct definition of GIS that I've heard of in a long time is now copyrighted by Esri, which is the main leading software producer for GIS software. And they call it the science of where, which I think is really appropriate, because it's figuring out not only where things are, but why things are there, and what kind of deep knowledge can we gather from understanding why things are where they are. So one of the things that Sarah mentioned that I specialize in is cartography. And so I'm just going to take a minute to explain why I think maps are so important. And I think I completely spaced on mentioning this. So in the definition for GIS, the last part of the sentence was that we do all of this to help in decision-making processes. And when you're analyzing data and doing visualizations, a lot of times with GIS, the end result is a map. And the reason that I think maps are so useful and important is displayed right here, sort of, partially right here. So this table is actually quite dated now. It doesn't feel like that to me, but it is, because it's world population from the year 2000. And from 2002. And I keep forgetting that 2002 is actually a long time ago. It doesn't feel like it. And so the table all the way on, or the column on the right, has world population in millions. It's kind of small. If you can't read it, don't worry about it. That's not important. But the important thing to get from it is that you have to sort of read through the table to get the basic information. You have to read through the entire table, or you could look at this map. And this map is called a cartogram. And so the top portion is the land area of Earth as we're used to seeing it, all the continents and the countries. The bottom map is the cartogram, and that means that the polygons have the country boundaries have been resized based on the country population. That's why Japan, which is this tiny little country up here, is huge over here. And China, which has a quite large landmass to begin with, is this medium green area up here. And it's just this huge area down here because it's been resized based on the country population. And so to me, a map is a way to convey a whole bunch of information really quickly. You can easily tell from this map which countries have the largest population based on looking at it, as opposed to having to sort through an entire table. So one of the things that I really love about GIS is that it is applicable to so many fields. I have chosen to use it in the field of environmental science because that's where my interests lie. Before I started working at Argonne, I worked for the village of Burr Ridge. So it's also used in municipalities to keep track of roadways, to keep track of, it's used nowadays at municipalities to keep track of a ton of their infrastructure, like pipelines and sewer covers, tree inventories. But aside from being used at the local and county government level, it's used in the military. In fact, the GPS satellite system that we now use basically every day in our phones was created for the military, and they eventually let the rest of us civilians get in on all the fun. But that system of satellites was initially created for military use. It's also used, it can be used in business from, for example, UPS and FedEx and other delivery companies can use road data and networking analyses to figure out which routes are going to be either the fastest or the most fuel efficient. Businesses can also use GIS and GIS analysis to figure out where they should build their next location. For example, Starbucks can look up Starbucks probably doesn't need to figure out where to build the next one, but they can look up the demographic information or the business information of areas that are doing well and try to identify similar areas that they should build another location. Emergency services, fire and police use it to find our homes or our locations if there's an emergency. It's used in public health to track not only spread of disease by humans, but also spread of disease by vectors. So I believe it's the CDC manages this really cool web map of mosquito and other vector-borne illnesses like malaria and dengue fever. And it's in a GIS system. It's got a mapping visualization component, and there's also information stored within that map that shows you like which specific counties, how many cases per county, and it's for a wide variety of diseases. There's also huge use in the environmental sector from monitoring and collecting observation data of where specific species are and other things. And these are just some examples, but this is one of the reasons why I think GIS is such a powerful skill set to possess, is because if it's something that interests you, you can apply it to pretty much any field that you desire. Now, to spend just a minute going into the technical stuff, when we're talking about GIS data, there's really two types. And if you have any familiarity with photography or graphics, you've probably heard of some of these terms before. There's raster data, which is more of like aerial imagery or things that are based on pixels that don't have a discrete start and end point. And then there's vector data that are, it's geometric data, and it has a specific geometry or length or distance to it. And then inside both of these is a separate file called an attribute table that lets us store all sorts of non-spatial information. So an example of this is census data. Every 10 years, the Census Bureau puts out a whole host of census data. And if you've never looked at census data, it's a lot, and it's very thorough. There's many different fields and really all sort of all sorts of information that you can pull out of there. But and it's used in so many different ways. And one thing that GIS allows us to do is to use all of that information that's extracted from census data and use it in more of a spatial way. So now, and for probably the last 20 years or so, when census information is released, they release the geometric file of census tracts and blocks, and so the polygons of all the different blocks and tracts and census groups, and then they release, God, there's like 100 different tables of different information. But then that's where you can start looking at geographically all of the information on, let's see, age, education, let's see, marriage status, like how many people have children at the census block level, let's see, how many people have gone to school, ethnicity, basically all of the demographic information that the Census Bureau collects, you can see in a map through the data that they release. For you young people, in the olden days, for the rest of us, not really that long ago, when you're talking about a map, you could have, especially if it was a village map or a land use map like this, you would have, your one layer of Mylar that had, let's say, parcels on it, zoning parcels, and then another layer on top of it, like separate physical layer that would have streets on it, and then maybe another third layer that would have buildings. And so that terminology exists today, where each separate category on a map is called its own layer. Even though now everything's digital, we still have adopted the name of when everything was physical and in paper. And so, really quickly, if GIS is something that interests you, there are multiple roles. So I've decided to be an analyst. I admire people that want to sit at a computer all day long and write software. I work with those people, but I am not that person. I would much rather have experts come in and use their statistical backgrounds to build a geostatistical tool that I can use, and then I can use those programs to create and run analyses that help provide information to other people. So there's software developers. There's also people who are data developers, that their job is basically creating and managing databases all day long, which that could be your thing too. Again, not really my thing. So I'm an analyst, but there's really something for everybody. And if software development is an interest for you, I know that the field of GIS is booming. It's not going away anytime soon, and there is definitely a need and an interest for there to be more software developers in GIS, and probably data developers, because we're always collecting data every single day on so many things. So in the environmental science division, where I work, we apply GIS in many, many different ways. For a long time, and in the last 2-3 years, there's been less of it. We've stepped back, but for many years, the bread and butter of my division was working on environmental impact statements and analyses as part of the National Environmental Policy Act, or NEPA. And we sort of worked as contractors for other government agencies and helped them work on these analyses whenever they were interested in developing or building something, or even thinking about building something on federal lands. So, and I'm actually going to talk about the one at the top, the Solar Energy Development, PEIS. Other geospatial activities that happen in my division, there's a very strong climate modeling group. And it's interesting because when you're a GIS person, scale is so much different, and you really see how everything is relative. So the climate modelers that I work with, their global climate models, their resolution is on the scale of like a 400-kilometer cell, and which is like multiple square miles. And now there's people working on trying to sort of resolve the discrepancies and the usefulness of something like at that scale with something that's at the GIS scale. If you're working in a city, or if you're studying the habitat of a relatively small area, a global climate model that's got a scale of 400 kilometers per cell, it's really not that useful. So now there's actually climate modelers who are working to refine that data and make it more useful at the sub-regional scale. There's also several studies going on that use GIS that just involve taking data. In terms of, I know there's the sagebrush and sage-grouse out west. We've had people go out and collect GIS data on that so that they can then model it once they come back into the office. And a lot of what's termed observational data is collected that way. For example, species, occurrence, and habitat, and things like that. So if I don't take too much time, I think there's enough time, I am going to talk about 3 different projects that I've worked on in the Environmental Science Division that involve GIS. The first one is the one that I'd mentioned. It's the Programmatic Environmental Impact Statement for Solar Energy Development in 6 southwestern states. And the final report is just as long as that title was. It's massive. And you'll see a theme, as I mentioned. A lot of the work that we do at Argonne, or my division does, is for other agencies of the federal government. So the first 2 of these projects were for the Bureau of Land Management. The last one was for the U.S. Forest Service. And so the solar PEIS was, we were asked at Argonne in the Environmental Science Division to help the Bureau of Land Management figure out where were the more ideal locations for solar energy development in California, Arizona, Nevada, New Mexico, Colorado, and Utah. There were several ways that we did that. So we worked with the Bureau of Land Management and got a whole bunch of data from them on where their land was. So we started with basically a GIS layer, the geometry of where all the BLM land was in those 6 southwestern states, which is a lot. I know the Bureau of Land Management is not as well known in Illinois and basically east of the Rocky Mountains or the Mississippi River, because there's so little federal land east of the Mississippi River. Most of it is private or state-owned. But out west, when you're talking Nevada, Utah, New Mexico, the BLM manages millions of acres of land. So I think the initial amount of land that we were looking at was about 72 million acres to figure out what would be suitable for either concentrating solar power or photovoltaic solar energy development. And they were interested in utility scale, so something that could provide megawatts of data, or megawatts of energy, not distributed generation. That would be solar panels on people's roofs. So the first thing that my colleagues did was they got solar resource potential data from the National Renewable Energy Laboratory, which is another Department of Energy national lab. And they screened it to remove everything that did not meet the solar resource potential threshold, and that was too steep. Because if it's too steep, it's more expensive to build on, and you have to do more to make it buildable. An interesting thing about this project and the NEPA process in general is that you're required to have stakeholder involvement. So after we drafted a report and worked with the BLM sponsors and their stakeholders, we also had to release it to the public. Well, not had to, but we released it to the public. There were a number of public meetings, so anybody from a non-governmental organization or a nonprofit organization to just a regular private citizen could come to these meetings and give their opinion and give their comments, and it was all recorded, and all of the comments were actually addressed in the final version of the report. But that's less about GIS. So after we did the first level of screening, we then, in the end, removed 32 other categories of exclusions that were determined by our sponsors and their stakeholders. Things like critical habitat or habitat for threatened and endangered species. Let's see, places that were already designated as protected, like wilderness and wilderness areas. Things like national parks and national forests. And another part of the NEPA process is that it's supposed to be very thorough. Well, I can't think of the right word, but it's looking at many different applications, or it's looking at how many different things could be impacted. So it's not just looking at threatened and endangered, or it's not just looking at how the environment could be impacted, it's looking at how people living locally could be impacted. We have to do environmental justice analyses. We look to see if there are what air quality and noise quality impacts could possibly be. It's a all-encompassing analysis. It's not just looking at one thing. So to do all of this, we ended up, aside from all of the analyses, one of the end products was this giant report, which we ended up making over 1,000 maps for. It was a lot of work. It took many years and many people. But so in the end, we made over 1,000 maps for this one project. And we also created what I think is a pretty neat interactive tool called Solar Mapper. And so this is one example of the maps that was created, and that was created to showcase this viewshed analysis that was done. So the thing about solar energy is that, and that's also wind energy, which I'll talk about next, is that they can be visible from quite a distance away. Wind farms are tall. They're looking at like 300-meter hub height now, which is really tall, or feet. Either way, it's quite tall. And with solar facilities, some of them are very tall, all of them are very bright. So it's not only if you are looking at something from far away, it's if you're looking down. If you're a pilot or in an airplane and you happen to look down, are you going to get blinded by this giant solar facility? Especially because this project took place out west, and in it's the border of California and Nevada, is one of the places that they've actually built a power tower, which is a type of concentrating solar power. And it's that thing that is, I believe, 300 feet up in the air, this giant tower, and at the top is a bunch of reflective mirrors that, and then at the bottom is just this a huge area of other mirrors at the bottom that just sort of bounce light back and forth. And so something like that gets incredibly hot and produces incredibly bright light to the extent that you could see it from, one of my coworkers went out, you could see it from 60 miles away, and it was still bright and it was still visible. So because of considerations like that, part of the NEPA process is including a viewshed analysis, which is taking into consideration the physiography of an area and looking at how far away you can see something. So this area, the 4 different colors represent different potential heights of solar energy technology. So one of the reasons that this was an important analysis to do for all of the sites that we were looking at is even though most of them were sort of in the middle of nowhere, a lot of them were relatively close to, you know, small towns in the area, or I know one of the sites we looked at was quite close to Joshua Tree National Park. And if someone is going to go to a national park, they don't necessarily want to have their view disrupted by a really bright thing that you can see 60 miles away. So we looked at the terrain of the land and the you know, how mountainous everything was to actually determine how far away these solar technologies would be able to be seen and how much they might be disrupting people's enjoyment of the surrounding area. As I mentioned a little while ago, another requirement for a NEPA analysis is looking at the potential socioeconomic impact. And I'm not sure when environmental justice was put into the NEPA process, but at least since I've been at Argonne. And we have to look at both the percent of the minority population and the percent of low-income population compared to the state average to see if the potential sites that are chosen would impact people of minority or lower income communities more adversely than the rest of the population. Basically, it's to avoid or to ensure that there's no intentional NIMBYism going on, or not in my backyard. And this is the website that I mentioned, the online mapping tool that we made, which is still out there and public if anybody wants to take a look at it. And it houses all of the data that went into this project. So people can look up the specific layers that we used. They can look up the specific exclusions that were used in the final report that were used to make these decisions. There's also, oh, and this is just an example of some of the different layers that are available. There's not only the presence of BLM land, you can see all the specific exclusions, you can see the layers as a whole, like where all the species habitat is, what is the exact solar energy potential of these specific locations. Let's see. There's also, and you are not going to be able to read this, don't try. It's just an example. There's a quite detailed reporting system that's built in so that if you choose this specific report, you can actually see what are the protected areas that are in the area that you select, whether it's conservation areas or a wilderness area or a specific type of species habitat. The next project I want to talk about occurred, the study area was basically the same almost as the solar project. This one covered the 11 western states of basically anything, I don't want to say west of the Rockies, but like from Colorado west. So like Oregon, Idaho, Washington, Wyoming, California, Colorado, those. We were looking at wind energy resources for the Bureau of Land Management, and we were trying to create basically an online map that they could use to help them make decisions and to help industry make decisions when they're trying to figure out where they could site a new utility scale wind farm. And the deliverables we had, not only the website, the WindMapper website, there's also a report that's relatively short, and then all of the data are available online. And so this is an example of the view of the WindMapper website. One of the things that we did was so an earlier report put out by the BLM determined what would be constraints to wind energy development. And so we had this whole list of things to work with, things that would either preclude development completely or make it more difficult. And so using that scale, we compiled a bunch of data and made these composite layers. So the blue would be areas that have a moderate level of siting consideration, which means you more than likely would be able to develop there. It would just be slightly more difficult, and there'd be some more hoops than normal. And then the darker brown areas are high levels of siting considerations, which means it would be, there's a lot more hoops to develop in those areas, and things that could result in mitigation, which would be having to do some sort of either a fee to pay for something so a classic example of mitigation is that if you're going to destroy a wetland to build something in one area, then you'll have to create a new wetland somewhere else in a similar area. So things like that. And this is just another view. The darker red areas, those were areas that had constraints that were just not buildable. So things like, again, critical habitat areas that had been designated by the Fish and Wildlife Service, or areas that were highly scenic as classified by the Bureau of Land Management, all sorts of things. I can't remember them all anymore. At one point, they were all in my head, and now they're just slowly fading to the back of my brain. Okay, the last project, and I don't want to take too long, but the last project that has a lot of GIS heavy work that I'm going to talk about is an analysis that we did for the U.S. Forest Service, yes, looking at renewable energy potential on lands managed by the Forest Service. And it was part of their strategic plan a couple of years ago, just to be able to figure out which of their lands would be most suited for these different types of renewable energy development. And we looked at concentrating solar power, photovoltaic solar, wind, biomass, and enhanced geothermal systems. And I'm just going to give a quick example of the GIS work we did for biomass, because there's a lot of trees in national forests. So basically the fundamentals of the models that we used was that we used the same process for each energy type. And we looked at, it was a screening level analysis. So not necessarily site specific, like I'm looking at this specific parcel of land, where are the best places, or what are the constraints here? It was more of a landscape level to look for potentially suitable areas. And we used GIS data from a variety of sources. For a lot of it, it was for, there were some criteria that were applicable to all of the energy sources that we were looking at. Like, there are some areas that are excluded based on just because they are. Like, if they were a especially designated area, or an inventoried roadless areas, which are all specific classifications of Forest Service land, they said up front, we don't want there to be any development on these lands, just take them out. For other energy sources, there were very specific resource-specific criteria. For example, wind turbines can impact radar for airports, or just radar in general. So we needed to be aware of where those sites were in relation to national forests, but no other type of renewable energy resource that we looked at really bothered radar sites at all. So we only needed those for the wind analysis. This is a lot of words, but basically, this is the stuff that we looked at for biomass development. Some of the things that we wanted to make sure that it wasn't too steep. Everything had to, the ideal land was less than 12% slope. Because we're talking about moving timber and the remains of timber from logging, logging and thinning residue. That's what it was, which is the stuff that's left over from logging practices. Since we're talking about actually moving things, we wanted to make sure that we were relatively close, or within 25 miles of transportation, so roads, rails, navigable waterways. We also wanted to make sure that we were relatively close to transmission lines, because if you're too far from a transmission line, then you're talking about building a transmission line, and that gets very expensive. And then other things. So that's just an example of the types of exclusions and considerations that we think about when looking at a suitability model, which is basically what this is. It's a suitability model for biomass energy. So this is what, the biomass data that we used, which I believe was put out by Oak Ridge National Laboratory. They have great expertise on biomass. So this is the initial area. This is the biomass data. And then when we look at the biomass data clipped to the Forest Service lands, this is what we're left with. So there's really high suitability in the Pacific Northwest, not so much in the Southwest. That shouldn't really be a surprise to anybody, because there's a lot of desert in the Southwest and there's a lot more rain in the Pacific Northwest. There's also quite a bit in the south over here. And so the results of this land were that we determined, how many acres were highly suitable, had medium suitability, and were really not that suitable overall for biomass. And the most suitable forest that we found was the Fremont-Wenema National Forest in Oregon. And that's just me going way too quickly through the suitability model that we did. Oh, if any of this interested you today, here are some GIS resources that might interest you some more. And if you really, really want to deep dive, so the software that I use at work every day is by Esri, which is the leading GIS software company I mentioned before. However, it is kind of expensive. So if you're interested and you thought, this GIS stuff sounds pretty cool, maybe I'd like to see if I can figure out how the software works. There's this really great open source version called QGIS. I mean, it's not exactly the same, but if you're just looking at playing around with some data or just getting a feel for what it might be like to work with GIS, it's open source and it's free, and it doesn't take up a whole lot of room on your computer. And with that, I would like to thank you again for asking me to be here today. This is my contact information, and I think I have cards somewhere if anybody wants to follow up with me later. And with that, I'm happy to take questions if anybody has them. Thank you. Oh, that's a really great question. So the question is, what are some of the challenges that I encounter every day with my job? So depending on what you do with GIS, like I said, some people make data all the time. They develop data, they maintain it. Because I work on a lot of different projects and not necessarily in the same region that I live in, I rely a lot on our sponsors or other organizations to provide data, especially if it's something like, their exclusion areas, for example. And so a lot of the times I have no control over data quality, which can be frustrating because there's really no universal or universally followed standard for data quality and for populating metadata. And so metadata is the data about the data. The software that we have contains this separate metadata file that you are supposed to include, the name of the data, what it is. So if you get it and nobody explains it to you, you're supposed to be able to figure out what this is that you're looking at. What it is, what it's supposed to represent, who made it. So if you have questions, you can actually ask somebody how old it is. If there's attributes in the attribute, or if there's fields in the attribute table, you're supposed to describe what those actually are, again, so you know what you're actually looking at when you see your data. Not everybody does that. So I would say data quality is probably one of the biggest challenges. Oh, the question is there a possibility for fraud? I would say, and I'm totally making up a number here, but I would say 99% of the time that is not someone's intention. I would say it's more about not necessarily thinking ahead that your data might be used by other people. It's sort of like when you're taking notes for yourself, and then all of a sudden you find out that you're supposed to actually share those notes with a bunch of other people. What you share with the public is probably not necessarily what you'd write down when you're just making notes for yourself. And so, but given that, I have heard stories from that I think it was during World War II, or during one of the wars, countries would actually put out false maps to hide where important things are, to encourage, or discourage people from going certain places. So I really don't think the intention is to mislead or to propagate fraud. And there's actually, if you study GIS more in depth, there are courses about ethics in cartography and not misleading the public or people with the maps that you produce. And it also sort of depends on what the purpose is of the map. So for example, I'm teaching a class right now in cartography at Joliet Junior College, and that's exactly what we talked about last week, is how the data that you're putting in a map might not actually be 100% accurate. It all depends on what the end product is for. So something that, for example, if you're making a trail map for people to go to one of the DuPage County forest preserves and to walk around on a trail, that data is probably going to be more generalized than someone who needs a street atlas because they work for DuPage County and they're trying to keep track of where all of the sewer and road infrastructure are. Like each scenario requires its own level of accuracy. Thank you for having me.